Let's get it started. Uh, Hello, everybody. How everybody is doing? It's a little bit rainy out in Bay Area, but generally overall nice. It's not that cold. Welcome to another edition of Yugabyte Friday Tech Talk. My name is Sushant Mishra. I'm part of the language layer and relation technologies team at Yugabyte. I lead various efforts related to query execution, transaction handling, and Postgres upgrade. And today we are here to talk about the insert on conflict uh, optimization and how we optimize the queries containing insert on conflict clause to provide better throughput and reduce latency. Especially this optimization is specific to the distributed system database such as YugabyteDB. Uh, we also have Jason Kim today with us. He has been with Yugabyte for around 5.5 years. Basically, he's a veteran at YugabyteDB and has been instrumental in developing a lot of different features and making this database work. So he will provide the overview of the use cases related to insert on conflict use cases and all the relevant details of this particular optimization. Before I hand over the floor to Jason, I would just wanted to have a quick note that this is our last YFTT talk for the year with the holidays coming up. We will again resume in the second week of January with new topics, and we will be making the announcements on LinkedIn and other media platforms for the details info on the upcoming YFTT talks. Once again, happy holidays and happy New Year in advance. And with that, Jason, the floor is all yours.
Yeah. So this is something, just to clarify, that something I've been working on the past few weeks, and also with Karthik Ramanathan. So let's get started. So today we're going to talk about what insert on conflict is, and then kind of display what things look like before and after the optimization that we made, do a demo, and then go over what cases the optimization is possible, do another demo, and finish off with some other remarks. So what is insert on conflict? Oh, let me show. Let's create this table, ABC, that just has an int as primary key, and insert a value 1 into it. So if we insert another 1 into this table, it will throw a duplicate key error. Unless, if we don't want that, then we can specify this on conflict do nothing clause to silently ignore such duplicates and do nothing. Alternatively, we can do a do update on conflict do update and take some other action and update that existing row into something else. This also works with unique indexes, like secondary unique indexes, not just the primary key indexes.
Jason, a quick question.
Yes.
What does the excluded means in this particular scenario?
It represents that we're referencing the existing row that was already that we were going to conflict with. Otherwise, it's kind of necessary. Otherwise, Postgres gets confused if you might be referring to some other I that might have existed.
Makes sense. So basically, there are two values of I, one which is already pre-existing on the row, and one which is provided as input in the query. And this excluded clause helps to kind of make that differentiation.
Yeah.
Yeah, thank you.
Yeah, so kind of want to display what things look like before the optimization we made. So we have some table ABC, same schema, but we insert values 1, 2, 3 and try to insert them again, but with an on-conflict do update. So the sequence of operations, we're going to first, for this on-conflict do update insert, we're going to try to insert 1, but first we have to read from the table to see whether it exists or not before we try to insert it. And we do that for all the values. So let me go through it. So here we have just a 3-node cluster, and the pre-existing values are 1, 2, and 3. And 2 happens to be on node 3, and 1 and 3 happen to be on node 1. This is just based on how they were sharded, which is just a hash. So first, we have to read to check whether 1 already exists, and we find that it does exist already. So then we have to take the do update action and update that 1 to a -1. So we do that, but Yugabyte already has an optimization to not send the right RPCs until we need to. So we'll just buffer them up for now. So we buffered up a delete 1 and insert -1. So when we get to the number 2, we have to, again, read from the table to see if 2 exists. But upon doing so, since we're going to read from the table and we had some buffered writes, we have to flush everything that we buffered before we do the read, just to get the most accurate data. So we flush that first, and then we do a read. And then since, again, this 2 exists, we take the do update action, and then we have to buffer up that update. Again, when we hit 3, then we have to read from the table, which means we have to flush our buffered writes. And then finally read from the table. We find it exists, so we have to do another update, which gets buffered. And then since we're done, we flush off everything else, everything that was buffered.
So Jason, basically all the rows which are being inserted, for each of the row, we do a read followed by a write, and that results in the number of round trips proportional to the number of rows which are being inserted without the optimization. So if I'm inserting 100 rows, then it results in 100 round trips between the Postgres and the storage layer. Is that the correct summary?
Well, so in this case, it's actually double the amount because we have to do both the reads and writes.
Yeah, so that is correct. Yeah.
In case we didn't have conflicts, or actually, even if we didn't have conflicts, we would still do inserts. And yeah, those would get buffered up. And then when we do the next read, it would cause that insert to get flushed out. So probably the only case that this could get reduced is if you have on-conflict do nothing, and you end up not causing any writes to get buffered. And in the kind of the, I don't know if you can say best or worst case, if everything conflicted and you did on-conflict do nothing, then you would just send a bunch of read RPCs, but no write RPCs.
Makes sense. So basically, the worst case is the number of round trips between Postgres and storage layer are twice the number of rows which are being inserted. In some scenarios, that can be reduced when we have a do nothing class. But proportionally, like if I have to put it in terms of the complexity, is still ON largely, apart from right, some edge cases where it may be a little bit reduced. Yeah, makes
Yes.
sense. Thank you, Jason.
Yeah, Jim nicely had a question about, yeah, does the update in non-conflict honor constraints? It depends on whether you specify that in your on-conflict clause. If I go back to this, so we specified an I in, it said on-conflict I do update. So this would look up any, it would only honor those constraints that have that exactly that I column. If there's any other constraints outside of that, then it would throw a duplicate key error as if you're not handling it through onConflict to update, do nothing run to update. And you don't need this specifier if you do a onConflict do nothing, in which case it would honor every single constraint, I believe. Yeah, there's another question. Can I see all of the
Makes
flushes
sense.
that are happening? Yes, we will demonstrate that later.
Thanks.
Okay, so with the optimization, kind of the gist of that is batching the reads. You'll see why that helps so much. So the batching process, it kind of goes in kind of 3 stages. One is processing the rows from input up to the batch size. The batch size is controlled by a JC variable we added called YB-insert on conflict read batch size. And then we do the batch read. So for each index that we're like that's involved in this on conflict, we'll send the read request for all the conflicting, like for every single thing related to the input in like a single read request for each index. And typically there might be just one index that we're checking, but it's possible for multiple to be involved in this. So we take that, do that read request, and then we kind of store this information in an in-memory map, which we then use during flushing, which is when we go through the rows we batched, and one by one we will take the appropriate action using the map, whether was it going to conflict or not, and then yeah, insert or do nothing or do update. And upon doing each of these actions, we have to update the map accordingly. Well, if it's a do nothing, then we don't have to update it. But if we're inserting something or we're updating something, then the map has to be updated.
Makes sense.
So yeah, let's go over what that looks like. So assuming the batch size is 3 or greater, then we'll send a batched index read to get every single, to look up 1, 2, and 3, and they happen to all exist already in the table. So yeah, that will be in our map, which I'm not showing, illustrating on this. But yeah, using that map, when we try to process, when we try to do the flush number 1, we find we have to take the on-conflict action, so we'll do an update. So we buffer that up. When we reach the 2 then and try to flush that, then also it's in the map, so we have to update it, but we just buffer it up. And the 3 also is buffered up. And then finally, we will flush whatever we buffered up and do all those updates. So this is a lot better. Not only are we saving on the read RPCs, but also there's more opportunity for the writes to get buffered up and not get flushed as often.
Yeah, awesome. Yeah, this is actually pretty cool. So basically, with the optimization, we reduced ON the number of round trips from ON to a constant, which maybe in most scenarios could just be only 2. And just to make sure we capture the details, right, to iterate the point which you mentioned, for all the rows we are inserting, we read them into a map, which is like an in-memory data structure. And then we just do the conflict checking with against that in-memory map while continue to update that map if there is a row gets modified, and also prepare the writes and put them in a buffer to kind of really do all the writes together in a one single request rather than multiple round trips. And this batching on both read path and the write path allows us to reduce the number of round trips, and that's the resultant of just 2 round trips.
Exactly.
Yeah, nice. Yeah, this is actually pretty cool. Yeah, awesome.
Yeah, so actually to show something, yeah, to show how cool it is, let's do a demo. So I'm gonna create a table that just has an int primary key, load it up initially with 1 through 10,000, and then we'll try to insert 1,000 to 2,000 without non-conflict do nothing. So this is going to insert 1,001 rows values. So I have here a RF1 cluster on a local build. This is a Alma Linux 8 FastDebug GCC build, so not exactly the same as a release build. So let me run this, but yeah. First, we're gonna run it with without the optimization, and then run it with the optimization, like with the batch size of 1024. And this is explain analyze this, so you can see, yeah. So the first one without the optimization, it takes 708 milliseconds, but with optimization, it only takes 15 milliseconds. And this is RF1, so this is not even the round trip time. This is all local. It's just even the RPC overhead is causing it to take so long. So imagine how much more effective it will be in a if this was like across regions, or like there was actually some like a cross node communication.
Yeah, this is actually pretty cool. So basically, with this optimization, the query start executing from around 3/4 of a second. It went down to around only 15 millisecond. And I think the most important thing which you earlier mentioned as well, Jason, the read request without the optimization are 1001, since 1,000 rows are being inserted approximately. And after with the optimization, all of that just got reduced to 1. And so this is like an astronomical benefit of this particular feature. And as Jason mentioned, if you have a distributed cluster or even a multi-region deployment, this feature will provide even more savings, because it essentially saves a lot of time, not only in terms of the processing in the software stack, but also in terms of the network IO round trips between the nodes, especially when they are further far apart.
Yeah, there's a question.
So the question is, do we also see a big performance gain with a multi-row insert with this new feature? So, let me know, Jason, if you want to provide an answer, or I can.
Like, I'm not sure if I understand the question. Like, we have, this is a kind of a multi-row insert, or is there something else?
So if I understood the question correctly, this is inserting into the table multiple rows. And at least what is shown on the screen, there is no on conflict clause. So this part
there was an
is
on-conflict as a
okay.
follow-up. There wasn't.
So Jason, we can continue. I'll kind of go through the question a little bit, and we can revisit it in a bit once we have the clarity on the question. Yeah.
There's
By
another
the way,
question on what a good batch size is. That's not something I've tested much, but right now, like we're just thinking of 1024, but that's just a kind of a shot in the dark. Well, we already have for pre-batching of like when we're for reads, like how much we fetch from a table, like at a time, like how much we fetch in one RPC at a time. At some point, it used to be default 1024. I don't know about now, but yeah, maybe that's the magic number. I'm not sure.
yeah. So we
going
are sticking with the 1024, but it can be tuned to higher or lower values depending upon the workload characteristic. Most of the workload we have seen generally does not really insert more than 1,000 rows in a single batch. So that's where we kind of chose the value of 1024. But yeah, it can definitely be tuned to higher values if there is a workload which is requires additional batching beyond 1024 rows.
Yeah, the thing with higher batch sizes, it may consume or it will consume more memory because yeah, you have this map that you're keeping track of for each batch. And well, this is a little more internal details, but part of that map, part of it gets freed up after each batch. So if memory is an issue, then you might not want to set it to an unlimited or extremely high value.
Makes sense.
Yeah, so when can it be optimized? So just going over when it works, primary key or secondary unique index, both are fine. Partition tables, we got them to work there. Returning clause, expression indexes, partial indexes, multiple indexes, they're all fine. And also generate columns. I guess the thing that we want to know more about is when it is not working, which is foreign relations calibrations. Well, those are, yeah, because we're trying to batch optimize for things that hit relations like that are stored in like other nodes. Yugabyte related. Well, yeah, calibrations. I don't remember the exact reason, but there was some issue there, and formulations. Formulations actually have this other batching that Postgres supports. Vanilla Postgres supports. Right now, we're just kind of keeping them separate from our batching. Yeah. Also, relations having row level triggers, so like before insert or after insert or instead of insert. But since foreign key constraints also are they're related with triggers, and that's a common use case, then we might try to allow that in the future. Yeah, I'm going to move on to another demo then. So this is a little bit more involved. We're going to create a partition table called parted, has int be bool, and partitioning by the Boolean column. So it can only create like two partitions, right? So for the false and for the true values. And load it up with these two initial values. And then it's going to create this trigger function. All it does is select count star from that table, entire table, and printed out as a notice. And we're going to set this on the part T partition only. So remember that we disabled the optimization for tables that have triggers, and so it will be disabled for this part T partition, but part F should still be valid and able to do the optimization. So I'm going to insert these 4 values with an onCompile do nothing. And I cut out the partition, the trigger definition part, just to save some space. And first, just going to go over what it looks like before actually demonstrating it. So remember, the steps are processing, batch reading, and flushing. So first, we will process the 1F. And yeah, since assuming the batch size is like some really high number, like 1024, we have to keep moving on because we didn't hit the batch size yet. So we processed a 2F as well. And then we processed 2T, but 2T doesn't support our this batching. So that's not good. We have to interrupt at this point and finish off our previous batch. So this means we do the batch reading of what we had so far, and then we flush each of them one by one. So the first one, it takes the nothing action because 1F already exists. The second one takes the insert action. And then we can finally finish processing this 2T since we're done with the first 2 values. And this involves doing the before trigger, which will print out how many rows are in the table so far, which should be 3 because we have flushed this 2F in step 6. And then actually do the write, since this 2T is not going to be involved in batching. So we just directly do the action for 2T, which in this case, since it already exists, is a do nothing action. And then finally, we can go to the last 3F. And since that's the end of the rows, then we can do the batch batch read of that and flush that. So this batch, it's as if the first 2 values were batched and the last value was batched, and the third one was directly handled. One other thing you might notice is that if we didn't do this interrupt in the middle, then this before row trigger, like if we didn't do this interrupt to handle the previous and finish off the previous rows, like this step 4, 5, 6, before handling this 2T, then the before row trigger would have returned 2, a count of 2 instead of 3. So this is kind of tricky. We have to make sure we flush out everything beforehand before we handle these non-batching cases.
Nice.
So this is the table. This is the demo. And yeah, it shows count 3 and inserts 2 values. And then another thing, this is not in the slides, is we can try to insert 100 values and put them in a random partition. Yeah, this is just randomly selecting true or false. So see how that goes. So this took 400 milliseconds. But if we do it with batching enabled, yeah. It takes 356. So the performance gain is not that high. And that's because we just keep getting interrupted by the even partition, which, yeah, it prevents our batching. We have to flush out what we batched so far. That's just something you have to be careful about if you're having cases like this.
Makes sense. So basically, in presence of triggers or the other bits for which the batching is not supported, that can interrupt with the batching and logic, and we kind of do a best effort in that case. So the gains are could be like incremental in that scenario. So yeah, I think that makes sense.
Yeah. Okay. Yeah, kind of finishing off with some remarks. So one of the big ones is there's a behavior change with this that comes with this optimization as well, which is related to this error message called cannot affect row a second time. So let's take this example of a simple table that has an int primary key. And if we try to insert 1 and 1 in the same statement with an on-conflict clause, before the optimization, it would insert 1, and then with that existing one, it would do update into a 1 plus 1 equals, which is 2. And with the optimization, we're going to start throwing this error for these cases. On-conflict do update command cannot affect row a second time. And this is actually the same as the Postgres error. So we're trying to get closer to what Postgres does. In case we had this additional one that already existed in the table before we ran this, then what happens is the first one would take the do update path and do a 1 plus 1, which is 2. And the second one would get inserted normally. So you would end up with a table that has 1 and 2. But this is also the case with our optimization and also with Postgres. So in both of these cases, we're kind of more aligned with Postgres, vanilla Postgres.
Nice.
Yeah, Jim also had a question of which version this feature is available. So this is still in the works.
So Jim, to answer Jim's question, we are targeting the early release of this feature in the EA release of this feature in 2024.2.2 release version of Yugabyte, which is expected to come out probably early next year. We will kind of coordinate on the exact timelines. I think that's a little bit TBD. But yeah, early next year, that feature should definitely be available. Just to clarify, EA means here that customers has to turn on this feature explicitly, or will not be enabled by default. But in the later releases, as this feature matures up, we will be enabling it by default as well.
Yeah, there's another question, but how are we doing
Jason,
on time?
a bit out of time. We can
Okay.
kind of to Patnaik's questions, we can respond in the thread for the video itself and kind of provide the explanation. I've noted down the question.
Okay. Yeah, just quickly finishing off. There's more tricky parts that are not shown here, such as self-referential triggers and with statements that contain an insert on conflict, and both of them at the same time. That just makes it really complicated. And returning clause is also kind of tricky. And we could extend this batching to the merge command in the future, possibly, is what we're thinking. Yeah, that's it. Thank you for joining us.
Yeah, awesome talk, Jason. Thank you very much for everybody for hanging around us. And just to reiterate, this is our last edition of YFTT Talk for this year. We will again resume in the second week of January next year. And happy holidays and happy New Year to everybody. Bye.
Happy holidays.